Hi everyone, welcome back to PRAKASAM tutorials. In this video, we are going to discuss about statistical independence of random variables. Consider two random variables capital X and capital Y with events capital A and capital B are defined as event capital A is defined as X less than or equal to X and event B is defined as Y less than or equal to Y for two real numbers small x and small y. The two random variables are said to be statistically independent if and only if the joint probability is equal to the product of the individual probabilities. So that is probability of x less than or equal to x intersection y less than or equal to y. So this term is also written as sometimes some of the textbooks probability of x less than or equal to x comma y less than or equal to y. And the statistically independent mean so which is equal to probability of x less than or equal to x into probability of y less than or equal to y. Okay, two random variables x and y are said to be statistically independent random variable. The joint probability density function, the LHS term is the joint probability density function is equal to the product of the individual probability. RHS term is the product of the individual probabilities. As the joint distribution function is uh, as the giant distribution function is statistically independent case, giant distribution function is fxy of x comma y is equal product of their individual distribution functions, that is fx of x into fy of y. Similarly, and the giant density function small fxy of x comma y is equal small fx of x into small fy of y. The conditional distribution functions for independent random variables, conditional distribution functions for independent random variables are given by fx of x by y less than or equal to y is equal, that is this is also denoted as simply fx of x by y is equal fxy of x comma y by fy of y. So using statistically independent random variable condition, this joint distribution function is equal product of their individual density function. Applying that condition to here. So after applying numerator and denominator, fy of y is the cancel. The remaining term is fx of x. Okay, fx of x is the marginal distribution function of the random variable x. So that is fx of x is equal fx of x by y less than or equal to y, or fx of x is equal fx of x by y. So similarly also fy of y by x less than or equal to x is equal fy of y by x is equal fxy of x comma y by fx of x. In the numerator term, applying the statistically independent random variable condition. Okay, so numerator and denominator fx of x is cancelled and the remaining term is fy of y. F x by y of x by y is equal fxy of x comma y by fy of y. So this equation already explained in my previous my previous video, that is conditional distribution function and conditional density function concept. So now we are the numerator term applying the statistically independent random variable condition. Okay, this is the numerator term is independent random variable condition, and after that numerator and denominator fy of y is the cancel and the remaining RHS term is fx of x. Also similarly fy by x of y by x is equal fy of y. So similarly the conditional density functions for independent random variables are also in the same process, similar manner. Fx of x by y is equal fxy of x comma y by fy of y. Now here the numerator term applying the independent random variable condition, that is fx of x fy of y divided by denominator term. Numerator and denominator term fy of y is the cancel and the remaining term is fx of x. Also fy of y by x is equal to fy of y. F x by y of x by y is equal fxy of x comma y by fy of y is equal. In the numerator term, applying the independent random variable condition fx of x into fy of y by denominator term. Numerator and denominator term fy of y is the cancelled. Remaining term is fx of x. Also, f y by x of y by x is equal to fy of y. This principle can be applied. Now here, the principle can be applied only to random variables. The same concept, same principle can be applied to any number of random variables for statistically independent or stochastically independent. Thus, two random variables x and y are stochastically independent or statistically independent if and only if their joint distribution or the joint density function is the product of their marginal distribution functions or marginal density function. So consider the joint distribution function case. The joint distribution function is equal to product of their marginal distribution function, and the joint density function is equal to product of their marginal density function. So this is the concept of statistically independent random variable concept.